what is the difference between equation on the top and equation on the second row?
First one is in integral form.
Second one. So they're pretty much the same, but the first one is applicable for one single point, which means differential form of equation, and the second one is applicable to a volume or a surface or a region, which is the integral form of the equation. So this is derived from this, and it's accurate. The reverse process delivering integral form of equation out of the point. It also could be accurate if we know everything about all points within a specific volume or a surface. So this is here, how this is called? Vector product. Vector product over a closed circle. Scalar product over a closed circle, and the name of this is circulation. Circulation of dot products within a surface equals to a rotation of the vector. And this here is a surface volume, a surface integral over an enclosed volume, and it will give us the currents flowing in or out. Okay. This is the same but applicable for the second equation with one very interesting condition here. If we can switch quickly between the frames, what is J here?
Electric current.
Electric current, exactly. And what is N here?
Magnetic.
Exactly, magnetic current, which we cannot observe with our current measurement means, but Maxwell added for full symmetry of equations. Yes?
Yes. So what does it mean intuitively, like magnetic current? Because, for example, the electric current is the motion of actual particles.
Yes.
But the magnetic current is like
the same. Motion of magnetic charges, which we don't see. We see only part of the universe. Magnetic charges we don't see, we don't know if they exist. But since the natural law of symmetry, smart people added this to the equations. So we don't see magnetic charges, but they make the equations complete, and they help us to solve more complicated
If
problem.
we wanted to have magnetic charges, then we had to add as well to the second equation of divergence of the magnetic field some charge.
Yes, that's why they added here. And if you mean this one,
Yes, the second.
yes.
So they're not symmetrical.
This is equals 0 means there is no point source of magnetic field by default. But if we find somewhere in the universe a magnetic charge, this can change to the density of the magnetic charge. The problem is we didn't have found so far. But if we look with the telescope and see, oh, magnetic charge there, immediately we can change this equation for this particular volume. So if we have a volume here, no electric charges, no magnetic charges, this will be 0, this will be 0. If we find the electric charge here, this changes to rho, and if we found a magnetic charge, this will change to something. Yes? Yes?
So this is why actually every field of magnetism is a dipole and never a point source.
Would you please repeat?
Magnets are always dipoles and never point sources of magnetism.
Not dipoles, but
Constants.
lines that close in itself.
Mhm.
Not in a point, but they close in. For electric charges, there is a regions where lines originate, area where the lines go through, and area where the lines go in. For magnetic, they're always close to itself, and this is why B always equals 0 in theory. And the Gauss law states exactly that the source of the electric field is the charge density, and if we take this into a volume, it will be the charge itself. And for magnetic field, divergence of magnetic field is 0, what we just discussed. And then comes the property of the medium. So depending on the what the dielectric fills in, what material fills in the volume that we are investigating, electric and magnetic inductance are a result of the reaction of the medium to electric or magnetic field strength. So we have field itself, reaction of the medium, and then the result is what we actually see.
Why do we say that those permeabilities are vectors? Actually, I think that they're in the most common case, like they're tensors or some sort of.
Yes, they're tensors. We say they are vectors or tensors if they react to time-varying fields. So something reaction of the medium is linear and uniform in all directions. Sometimes the reaction of the medium is non-linear, depending on the frequency and the field strength. That's why sometimes is denoted as a tensor. In general, for weak fields, slow varying, the constants are constants and they're real numbers. But if we have time varying field, and the medium can react in a specific manner, which is
Maybe when it isn't isotropic, so it reacts in different directions.
Different way,
then it
yes.
is a tensor.
yes, anisotropic maybe. Like most of the ferrites are anisotropic, that's why permeability is denoted as a tensor quite very often. And yes?
I'm sorry. So if there is a vector that influences a time varying field, we can describe it as a tensor.
Yeah.
Is it good?
The reaction of the field is described as a tensor.
The reaction to field itself.
Yes, and this epsilon and mu are the reaction of the field, of the milling. And there is one beautiful theory emerging, which is kind of contradictory, but it says that the vacuum is not a vacuum itself. It's actually space filled with particles. And the reaction of this particle to the field is what actually we see here and described with this constant. So this 8.8 times 10 minus 12 farads per meter is the reaction of the guy told neutrino field space, which kind of makes sense. It's not something that is just a meaningless thing. And so is the magnetic field. There is always 4 pi something, 4 pi something else, which is related to the circular things. Something is caused by a circular dimension. You know, this 4 pi is not for no reason. If it was for no reason, it will be some unimaginable number that came out of nothing. And this comes from the circumference of a circle, which is apparently things are somehow connected into the universe, each to other, but we simply don't know. Or and this is the phasor representation of harmonic field. Phasor is when we have the complex magnitude of a vector plus the time varying component. And this is the time varying component. And we can apply derivation. First of all, why the complex numbers are introduced? They're introduced for one single reason: to simplify the operations. There are things that don't exist, nobody cares about them, but they are put here for one only reason: to make subtraction, division, multiplication, derivatives simple. On the bachelor's class, they told me, sir, if you involve complex numbers, we are leaving. Things should be as simple as possible, but no less. Oh, I forgot to translate the topic in English. So if we imagine that there is only electric charges, and we we will take into the account of this condition that divergence of h vector is 0, which we assume that it is. It means that h vector, magnetic vector, can be represented as a rotation of some imaginary vector. Did you grasp that concept? As far as we discussed, there is no point sources for magnetic vector. Right? Right. We know only charges which are responsible for the electric vector. For magnetic vector, no charges. So divergence of h vector in each point of the space is 0. Right? Right. And if we are confident that in each point of the space h vector is 0, then using the mathematical trick, we can assume that the magnetic vector is a product of another vector, imaginary, which rotation in space causes the magnetic field.
Okay.
And we call this vector a magnetic vector potential. Okay? Okay. And we can deliver now the magnetic field simply. Just apply operational rotation over our imaginary vector, and we get our magnetic field. And then we can put this magnetic vector everywhere in the Maxwell equations where we need it. Like here. And if we skip the charge part, the part causes by charges, we can see that, this is from this equation, we can see that knowing the A vector, we can deliver also an expression for the E vector. Did you get the point? No?
I had a question about the vector potential. I don't understand why it's divided by the magnetic field. Why not just describe as or assume that the curl of A without dividing by
Which line do you mean?
the third line. Nabla dot H equals 0.
Nabla H equals 0. Yes, very good question. Nabla H equals nabla dot H, which means divergence of H vector, magnetic field. In plain Bulgarian means that there is no point sources of magnetic field.
There is no monopoles.
Yes, no magnetic monopoles.
But I don't get the second part. Like why?
The second part is what mathematicians love. Because if there is no magnetic monopoles, then magnetic field everywhere can be described as a result of rotation of some other vector.
Okay, but why it's divided by or multiplied by 1 over 2?
Why over 2? Because nabla A equals, nabla cross A equals B, and B equals H times mu. That's why we have to divide it by mu.
How is like a conversion factor between H and B?
Yes, mu is the reaction of the medium to the magnetic field.
Oh, I see. Okay. Now,
If you measure a coil, you will see what B causes. But B is the reaction of the medium to H.
the reaction. Okay.
So smart people introduces the vector A, which is even more abstract than the complex numbers. You know, nobody has measured this. Nobody. No one. But since it explains the theory in a beautiful manner, it is kind of adopted. And adopted so much, then if we get this and put it here, we get over here. This is derivation of E in time, the change in time, equals to rotation of this nice vector. And if we solve this equation, we get to expression of E vector, which equals time derivative of A minus some constant. So, to determine the E component and H component of the field, we need to know only one vector. This is the vector A. And then we can get the field components. Very good. The problem is how to find the A vector. The rest is easy. And now, once we have the expression for E vector as a result of our magnetic vector potential and the constant phi, combining these two equations, we get to this expression here. Cross product blah blah cross A, which means rotation of the vector A plus some time variation of the vector A equals to the current density J, which should be read in the reverse order, which means that if we have a current flowing somewhere in the space with current density J, it will cause this process here. And some smart guy delivered the vector identity, this one. Rotation of C equals to nabla divergence of C minus nabla squared C. So this is vector identity, which means nothing but a fact that somebody has proven long before us. So we don't have to prove, which is good because we get lost. And applying this vector identity to our equation that we delivered so far, we get, this is in more intelligible language, rotation of C gradient divergence of C minus gradient squared of C. Applying this to that, this is the identity plot, we get, bless you, we get to this more simply looking equation. Very simple.
Very simple. Yeah.
Which is good. Why is good? Because we have a clear view what is the cause and what is the effect. And now we just have to substitute the reaction of the medium and time variance, and we can say this to be called beta. And beta in the real life is the phase constant of a wave, propagating wave. Means how many degrees or radians the wave will change the phase if it propagates on 1 meter distance. This is what beta is. And here we have the full beauty of the equation. The cause, current flowing somewhere in the space, causes something with our imaginary vector A. And our imaginary vector A, once we know it, we can go back few slides and determine H component of the field and E component of the field.
Then what is this calibrator?
Lorentz calibrator is because if you solve differential equations, you will get a set of infinite number of solutions. And Lorentz calibrator tell us, pick this one.
Uh-huh.
So basically, because this vector potential that we chose, we don't measure it, and it turns out that whatever of those solutions we plug in, we get the same results as physics.
Yes.
And I think if we don't do this calibration, maybe we have
Other-
more
Other possible
additional-
mathematically true solutions which are impossible to exist.
Yeah, but the cool thing is that we used the scalar potential to define it. Otherwise, I think we would get a more complicated equation.
Yes. Basically, this tells us solutions is just this set of, let's say, surfaces or lines, depends on whether it's solved in 2D or 3D. Calibrator tells us, take this set of solutions. Why this work so? Nobody knows. But that's how everything in modern electrodynamics is explained. Yes. And here comes the beauty part. What do we do see here?
in this case, maybe we imagine it that there is no electrical source of charge, and that we have magnetic charges.
Yes. And then?
Well, we saw that in the first case, in reality, the way that we write Maxwell equations, they're not fully symmetric, so we basically reverse that symmetry.
Yes, yes.
Go.
Mohamed, you.
Yeah, I was gonna say the last equation, does it mean presenting magnetic field or magnetic charge somewhere
Yes.
will affect our imaginary vector F, like the last slide?
Exactly. So what we did here on this slide. Here we pretended that there is no electric charges. There are only magnetic charges that we describe with them. And then, identically to the previous over here, conclusions that we make over electric charges, we apply exactly the same to the magnetic charges. And we get to the point that instead of vector A, we can use imaginary vector F.
So why do we do this? How does this help us solve some questions?
Because we are very good in maths and love to play with numbers. There is no at least no observable physical effect.
So we try to find the symmetry, and maybe this will help us in the future with some new discoveries.
Actually, not in the future, but in the
Right.
present. This is just mathematical manipulation, which is mathematically true, physically unobservable directly. But indirectly, this is exactly what we are getting out of under some conditions. And that's why this theory is not discovered. And we prove that in this way, that if we have a magnetic current density, it will result to the vector potential, electric vector potential F. So if we have a magnetic charge density and it flows in time and space, it will result to electric vector potential F. And what is so important to magnetic vector potential F? What is so special? What was the special about magnetic vector potential F? The good thing is that if we know it, we can determine
The initial point.
the field components E and H, bless you, which are actually the fields that we can observe. So we cannot observe A vector or F vector, but if we know what is the cause, we use this interim solution and deliver something that we can observe. And we have two cases. Either electric excitation of flowing charge, electric charges, either magnetic excitation of flowing magnetic charges. So if we have either of them, we can get the field in any point in the space.
Yeah. Okay.
So this is the reason why we are and if we write down the things that we were discussing so far, there is a beautiful symmetry set of equations formed. B vector, E vector, and how it is delivered from the current, electric current, D vector and H vector, and how it is delivered from magnetic current. So we have to know either electric currents, either magnetic currents. Knowing them, we know everything.
So the vector potential is something like mathematical mediator between the current, whether it's electric or magnetic, that we measure, and the field that caused the current.
Yes, exactly. I couldn't say it better. So this is help to our weak minds to find the relation between current and electromagnetic field. Obviously, there is no direct relation. It is relation through auxiliary vector field that we cannot measure, but just using it as mediator. The essence is knowing J, the electric current, we can establish E and H, and knowing M, magnetic current, we can establish the H and D. And now, an example. Actually, not the example, but the actual solution, how it is delivered. Having this equation of only current flow in one axis for simplification, not three-dimensional, one-dimensional, will result for a vector potential like that, and this equation is called Helmholtz equation. And somebody solved it before us and delivered the solution. That the solution of this one is this thing here. Triple integral of a volume of G, this is called Green function, times the current integrated.
Question.
Yes?
This vector A, Z, is it a vector or is it just a scalar in this case?
It's a vector. It's a vector. Vector and forms a vector field in a space. Easy. So knowing the current, we get the auxiliary A vector. And same is applicable for the magnetic current and magnetic charges. Knowing them, we can determine the auxiliary vectors in a specific point. And this is not the complete solution. It's also approximate solution, and I will tell you why. But for the sake of simplicity, 99% of the cases is described like that. There is no relativistic effect involved, which actually exists. First. And second, there is because of the time of propagation, when charge moves here and forms a current, the effect takes time to happen here. And this is not taken into account into the equations. They assume that everything happens in the same time, which for the short spaces is true, almost true. But if we examine the things in a larger scale, this is not true. And there should be a correction involved for the time of propagation.
And here the solution is green function.
Yes.
Can you look at the previous slide? So know how this green function looks for this specific equation?
For this specific equation, there is a specific green function that solves it. If you change something, the solution also changes, and you have to hire mathematicians to tell you this is the, the function that you need for your case. So for a linear source, J goes to I, and the volume integral turns to a linear integral.
I have a question. So if the relativity was taken into account in this equation, it would look a lot more complex, right?
Yes.
Has it been done already, or?
Yes, but it's almost insolvable and just for mind games. Because the reason is, since we deal with things that are in our reach, within our reach, we don't care very much what happens in picoseconds before or after. That's why we assume that no time-space effects happen. Basically, nobody cares. Or can measure.
Well, it might be significant for very far off objects, like in space.
Of course, but we don't know the exact solutions, and that's why we observe something and make theories, but we are not quite sure about this. And that is how we deliver the A vector from a current and E and H vector from A vector. Very beautiful, right? Simple. And once we want to get them to our real coordinate system and real numbers, not involving complex numbers, we get this set of time varying harmonic sets, which are basically well, not so complex actually, because higher order components get neglected, and we work only with the first and second. Yes.
Okay, I have a question about the last two things. First is basically the Helmholtz equation tells us how this electromagnetic wave propagates, right? Or-
Yes.
Okay, so
Not the wave, but the A vector.
oh,
A and
yeah, that's
F.
different. And still, we say that if we were to take the time, if we were to take further distances into account, it would make it more complicated because of special relativity. And yet, in those two equations, we neglect the terms proportional to 1 over r squared.
Yes. Because
I
two
guess
are far away from us, and we don't care about it.
So we can do both. Not account for special relativity and neglect those. There's something that bothers me there, but I still don't.
Yes, but we can measure only things around. We cannot measure things that are far away. And because we cannot measure things far away, we don't care about them. And also for this happens now, but will affect something after several picoseconds. In 99% of the cases, we don't care about this time delay. We think that changes happens instantly for the sake of simplicity. If we add this to the equation, this may change nothing or may change something. But I haven't seen anyone in the literature that investigates this. Maybe the effect is negligible, who knows? This is the problem when we don't develop science ourselves, but rely on somebody else to do it for us. He tells something, and we have to either trust and take it, or distrust and prove it wrong. It's like the history. History is written by the victors. And the victors put one in the books. You have either to accept it and keep quiet, or dig for yourself and find the truth for yourself. Here is the same.
Well, who do we trust in this case? The mathematicians? I mean, they.
Oh, the physicians.
Well, they tell we have a large hadron collider,
Yeah.
and we produce this paper. Trust me or prove me wrong, and because you cannot prove him wrong, they say,
So they say
trust,
that it is
man.
insignificant, this effect is insignificant,
Yes.
according to.
According to them, yeah. That's what they say, prove me wrong. Even very simple things, like, the Coulomb force with electric and magnetic charge. If you don't have a setup to reproduce it, you have to either trust the scientists before us, or be resentful but keep silent because you cannot prove them. This is the problem of small countries. We cannot reproduce everything and write it for ourselves. We have to rely on larger. Maybe I shouldn't tell this. Here is a current, small dipole. I will skip that. And this is the translation from Descartes to spherical polar coordinate system, which is our natural coordinate system. We work in polar coordinates, but use Descartes because it's more simple. And that's how the current flowing here translates to vectors in every position into the space. And that's why this is the essence of everything, because that's how radiation of antenna is determined. If we have a dipole here, on the arms of the dipole a current is flowing, then using these things we can determine the field in any position around the dipole. And if we substitute the dipole with a more complicated antenna, we can do the same.
So it is working, but we don't know exactly how.
Yes. We almost know. We almost know. And based on that derivations for the field, 3 zones of radiation are formed around the radiating current. The first one is called the reactive zone. Which is very closely located around the source. And if we stay there, we will feel a fast changing electric field, like staying between the plates of capacitor. So you will see just electric field up, then down, down, and down, and down. This is called the reactive zone. If we get further away, and this reactive zone is from 0.0 up to 0.62 of the one of the dimensions of the antenna over lambda. So this is the kind of a limit of the reactive zone. So there is no flow of energy in this zone. The next zone is near field zone. This is the generally accepted limits of this zone, where there is direction of the electromagnetic field, energy is flowing out of this zone, but antenna pattern is not formed yet. So if you're too close to the antenna, you will see some energy coming, but no antenna pattern formed. Or pattern change, there will be a pattern formed, but will change if you change the distance. It will look like something else. And then is the far field zone where we work. Or Fraunhofer zone, where we have formed pattern which doesn't change with our distance to antenna, and there is no Z component of the field. In all other zones, reactive and near field, there is a component of in the direction of propagation, a vector, but in the far field, if you're too far away from the antenna, there is no more component of E vector along the direction of propagation. So these are the 3 distinctive zones, and that's it for the electromagnetic foundations of radiation.